Welcome to Chapter 13 on Dimensionality Reduction. Here we learn how to represent data with far fewer features while keeping the information that matters. Consider that a single handwritten digit, scanned at a modest 28 by 28 pixels, is already a point in 784 dimensional space. This chapter builds the topic up in stages. By the end of this chapter, you should be able to explain why dimensionality reduction is useful and when to apply it, describe the curse of dimensionality, distinguish feature selection from feature extraction, and grasp the intuition behind principal component analysis. You should also be able to describe principal components and explain variants, use PCA for both visualization and preprocessing, explain why features must be scaled first, and understand what TSNE and UMAP are good for. This figure shows the core idea. PCA finds the directions of maximum variance, here labeled PC1 and PC2. Projecting onto PC1 alone compresses two features down to one while keeping most of the information. So, what is dimensionality reduction? It is representing a data set with fewer features than it started with, while preserving as much useful information as possible. It lets us visualize data, reduces noise, and speeds up training while shrinking storage. It can also reveal hidden structure that was buried in the full feature set and reduce overfitting by removing redundant inputs. The catch is that reduction always discards something. A dataset is high dimensional when it has many features, and such data is everywhere in modern machine learning. Think of text, where each word or phrase becomes a feature, easily tens of thousands. Images, where every pixel is a feature, genomics, with thousands of genes per sample. Customer behavior, where every action adds a column. And finance, with many indicators per firm. All that width can encode genuinely rich information. The curse of dimensionality names a cluster of strange problems that appear as features grow. Data becomes sparse, computation grows expensive, overfitting becomes more likely, and distance measures grow less meaningful. On top of that, visualization becomes impossible without reduction, and you need far more training data to cover the space adequately. Dimensionality reduction is one of the main tools for fighting back. There are two fundamentally different ways to reduce dimensions, and the difference matters for how we interpret the result. Feature selection simply keeps a subset of the original features and discards the rest. Feature extraction takes a different route. This contrast, feature selection versus feature extraction, is the distinction worth holding on to as we go forward. Principal component analysis, universally abbreviated PCA, is the most widely used dimensionality reduction method and a sensible first thing to try. Its first principal component points in the direction of greatest variation, the axis along which the points are most spread out. PCA serves for visualization, noise reduction, compression, preprocessing, and understanding the major patterns of variation in a dataset. One more point worth stressing: PCA is unsupervised. Strip away the linear algebra, and PCA is doing something visual and simple. It finds the natural axes of a cloud of points. In higher dimensions, it does exactly the same thing, finding the directions of greatest variation in order and letting you keep the top few. This figure lays out the PCA pipeline: standardize the data, build the covariance matrix, extract its eigenvectors, which are the principal components, keep the leading ones, and project the data onto them. A principal component, then, is a new variable formed as a weighted combination of the original features. Because the first few components soak up most of the variation, a dataset with many features can often be faithfully represented by just a few. So how do you know how many components to keep? PCA can feel like a black box of covariance matrices and eigenvectors until you run it once on numbers small enough to hold in your head. Here, a reviewer rates 5 gadgets on 2 qualities: a design score and a performance score, each from 0 to 10. These are our 5 gadgets, rated on 0 to 10 scores. Both means equal 5, and the last 2 columns show the centered values. That is, the scores with the mean subtracted out. With the data centered, we sum the products of the deviations. The two features have equal variance of 2 and a strong positive covariance of 1.8, the numerical signature of points stretched along a diagonal. The principal components are the eigenvectors of the covariance matrix, and their eigenvalues tell us how much variance is captured along each one. Each eigenvalue is the variance along its component, so the fraction of total variance a component explains follows directly from it. Formally, the explained variance ratio of a component is its own eigenvalue divided by the sum of all the eigenvalues. Here, the total is 3.8 plus 0.2, which is 4. So the first component explains 95% of the variance and the second just 5%. To get each gadget's single PCA coordinate, we project its centered vector onto the first component, which here is simply the two centered values added together and divided by the square root of 2. Each gadget is now reduced to a single number, its position along the first component. Gadget 4 scores highest, strong on both qualities, while gadgets 1 and 2 score lowest. These 5 numbers are the compressed dataset. This figure shows the PCA by hand. The 5 gadgets stretch along the 45-degree diagonal, so the first component runs through the mean along that long direction, capturing 95% of the variance, while the second catches the small leftover. PCA, like every distance and variance method in this book, is acutely sensitive to scale, and forgetting to scale is the single most common PCA mistake. Since PCA chases the directions of greatest variance, the remedy is to standardize every feature first to mean 0 and standard deviation 1. Here is the key point. Always standardize your features before running PCA. An unscaled, large-numbered feature will hijack the first component by virtue of its units, not its importance. Scale first, then reduce. One of PCA's most beloved uses is making the invisible visible. Reduce a 30-feature medical data set to 2 components, plot them, and color by class, and you may suddenly see the classes pulling apart into distinct regions. PCA also serves as a pre-processing step ahead of a predictive model. As pre-processing, it offers fewer features to train on, less noise from discarded low-variance directions, faster training, reduced multicollinearity since the components are uncorrelated by construction, and better performance for some models in some cases. But PCA is no guaranteed win, and here is the subtle reason. PCA is invaluable, but not universal. It captures only linear structure. Its components are often hard to interpret. It is sensitive to scaling. It ignores target labels, and its high variance directions are not always the most useful for prediction. When the structure you care about is nonlinear, a ring or a spiral or a curved manifold, PCA's flat projections fall short, and the methods in the next sections take over. TSNE, short for T-distributed stochastic neighbor embedding, is a nonlinear method built almost entirely for visualization. Its local focus makes it great at pulling apart clusters PCA leaves overlapping, but distances between far apart clusters on the plot are not meaningful. Be careful. A cluster's visual size does not reflect its real spread. Results shift with settings like perplexity, and it is heavy on large datasets. Use TSNE for spotting local clusters, never as pre-processing for a predictive model. This figure shows how TSNE preserves local neighborhoods. Points close together in the high-dimensional data stay close in the two-dimensional embedding, pulling apart into well-separated clusters meant mainly for visualization. UMAP, short for Uniform Manifold Approximation and Projection, is the more recent cousin of TSNE and increasingly the default for nonlinear visualization. The same warning applies. Visual clusters are a hypothesis, not a proof. These three methods serve overlapping but distinct purposes, and a quick comparison helps you pick the right one. This table compares the dimensionality reduction methods side by side, summarizing where each of them shines. A reliable habit is to reach for PCA first, since it is fast, transparent, and doubles as pre-processing. For our Python practice, we will use the digits dataset from scikit-learn, 1,797 images of handwritten digits, each an 8 by 8 grid flattened into 64 pixel features. This code loads the digits, standardizes the 64 pixel features, reduces them to two principal components, and then reports how much of the total variance those two components manage to keep. In short, we standardize the 64 pixel features, then project them onto the first two principal components. Now we scatter those two components and color each point by its true digit. This code draws that scatter plot, placing the first component on one axis and the second on the other, and coloring every point by the digit it represents. Even with just two components, several digits drift into their own regions of the plot, while the visually similar ones overlap. To use PCA for pre-processing rather than plotting, you need to decide how many components to keep. This code fits PCA on all components, plots the cumulative explained variance, draws a line at the 90% target, and prints how many components are needed to reach it. The dashed line marks the 90% target, and the printout reports how many components it takes to get there, far fewer than the original 64. Finally, let us use PCA as a pre-processing step and check whether it actually helps a classifier. This code builds a pipeline that scales the data, applies PCA keeping 90% of the variance, and then fits a logistic regression before reporting the accuracy on a held-out test set. Asking PCA to keep 90% of the variance tells it to retain just enough components to reach that level, automating the choice we made by hand earlier. For contrast, here is tsne on the same digit data. This code runs tsne to embed the scaled digits into two dimensions, then scatters the result with each point colored by its true digit. The 10 digits usually appear as 10 well-separated islands, far crisper than the PCA plot. In this case study, a retail company tracks wide-ranging behavior for each customer, dozens of columns wide, far too many to plot or eyeball. Before any model, the team wants to understand the shape of the data and whether customers fall into natural groups. This is a natural home for dimensionality reduction. The workflow first cleans and standardizes every feature, since the columns live on wildly different scales, then runs PCA and inspects the cumulative explained variance. Next, plot the first two components for a fast overview, apply the clustering methods of Chapter 12 to the reduced data, bring in tsne or UMAP for a sharper, nonlinear view, and interpret the picture with business knowledge before acting. The team might find customers with similar buying patterns gathering into recognizable neighborhoods, hinting at segments like loyal, high-frequency shoppers. Two cautions, both straight from the theory, are worth repeating. The code below uses the digits dataset as a proxy for high-dimensional customer data and demonstrates how quickly PCA compresses features while preserving most of the variance. This code reports cumulative variance for several component counts, then compresses the data to 20 components and reconstructs it, measuring the reconstruction error to quantify how much information was lost. With 20 components, the digits data retains the large majority of its variance, and the reconstruction error stays small, showing that PCA achieves meaningful compression without discarding the structure that matters. To summarize, dimensionality reduction shrinks the number of features while preserving the information that matters, and principal component analysis is the linear workhorse of feature extraction. For further reading, look to the original paper that introduced tsne for nonlinear visualization and the paper presenting UMAP as a faster, topology-preserving alternative. That brings us to the end of Chapter 13 on dimensionality reduction, where we learn to compress many features into a few while keeping what matters.